Hello, Calculus 12 students. I wanted to make another lesson video. This time I wanted to cover the topic on concavity. And when I'm talking about concavity, this basically means we're talking about the shape of the graph. Okay, and the good news is when we're talking about the shape of the graph, we basically just have two options. The two options are we have concave down, which looks like this. So it kind of looks like a parabola that's opening down. So this is called concave down. And we also have another shape called concave up, and that means your graph will be opening upwards. So this represents concave up. And throughout this video, instead of writing concave down and concave up, I'm just going to use the letters CU and CD. All right. So basically, throughout this lesson, I want to find where my graph is concave up and concave down. And in order to do that, I need to look at my second derivative. All right, so here's some rules for concavity. If I have my second derivative here, and if my second derivative is positive for all x values on this interval AB, then that means my graph will be concave up on that interval AB. Okay, so if my second derivative is positive, then I'm looking at a concave up situation like this, so my graph will behave like this. Okay, and if my second derivative is negative for all x values on the interval AB, then that means my graph will be concave down on that interval. So basically my graph is taking the shape of this form on that interval if my second derivative is negative. And finally, if my second derivative here is equal to 0, that means I have a point of inflection. So the point of inflection, this basically means that I'm not concave up or concave down. So I'm not concave up or concave down. So let me just kind of give you a little diagram of what that looks like. If my graph looks like this, basically this right here would be an inflection point, IP. So that means this red dot there, that basically means I'm not concave up or concave down. Clearly, if in this region right here, this yellow region, I'm concave up, and if this graph actually continued, if I just extended that, then that would mean I'm concave down here in that blue part. But this red dot in the middle there, that means I'm not concave up or concave down. All right, and that happens whenever my second derivative is equal to 0. Okay, so that's the theory for concavity. Let's go ahead and now apply this to a few problems. I'm going to go ahead and just erase this so I have a little bit of room here. And one of the basic kind of questions in calculus is that we just give you, a regular polynomial here, f of x equals to x cubed minus 3x squared. And basically we'll ask you to analyze this. This time I want to find all intervals of the function where we're concave up and concave down. Okay, so if I'm looking for intervals where I'm concave up and concave down, then I need to analyze my second derivative. Okay, so going back to the notes here, let me just erase all this. Once again, if my second derivative is positive on a given interval, then that means I'm concave up. And if my second derivative is negative in blue, then that means I'm concave down on that interval. Okay, now just before we start doing the algebraic work here, I do have a graph of my polynomial right here. So this is the graph of, f of x equals to x cubed minus 3x squared. And if I look at this graph right now, it looks like this part of the graph right here, yellow, that looks like my graph is concave up. Okay, so if I look at this region onwards here, it looks like this, it looks like this region right here, that region in green there, it looks like I'm concave up. And if I look at this region here in blue, highlighted in blue, it looks like the graph from this part to that part, it looks like we're concave down. All right, so just by looking at the graph without analyzing any derivatives here, and if I just look at the picture of the graph, I have a pretty good idea of where the intervals are where I'm concave up and concave down. All right, so now let's go ahead and let's just show this algebraically now. So that's part number one. So for part number one, I will do this question just down here. And if I want to find the intervals where I'm concave up and concave down, we need to analyze our second derivative. So if if I want my second derivative, I need to analyze the first derivative. So this is going to be 3x squared minus 6x. Okay, and then my second derivative, f double prime of x, that's going to be 6x minus 6. Okay, and now what I want to do now is I want to determine whether if my second derivative is positive or negative. So basically, what you need to do in order to establish that is you need to set up an interval. So before you set up an interval, you need to take your second derivative and set that equal to 0. And whenever you set your first derivative or your second derivative equal to 0, go ahead and factor your derivative expression here. So this will be x minus 1 here, and that means my value of x that makes this equal to 0 will just be 1. Okay, so I just look at that point, right, this situation here, and my x value must be 1. Okay, so let's go ahead and just draw a number line now. So here's my number line, and here is my value of 1 here. Now this 1 here, this value 1, that's not a critical point because this is my second derivative, and whenever you're finding your second derivative and setting that equal to 0, what you're really doing is you're actually finding your inflection point right here. Okay, so whenever you take your second derivative and set that equal to 0, you're finding your inflection point. So I will say that this is like an inflection point, the x coordinate of my inflection point, and this is my second derivative right here, f double prime of x, and that's going to equal to 6 bracket x minus 1, which is that guy right there. And let's go ahead and analyze this now. If I pick an x value that's to the right hand side of 1, maybe like the number 10, if I plug in 10 over here, that means I get a positive expression, so this will be positive. Okay, so what that means is that my second derivative here is greater than 0. I'm positive right there. And if I pick a number to the left hand side of 1 in that blue region, maybe I'll pick maybe 0. 0 is a very safe number. If I plug in 0 back into my second derivative now, if I plug in 0 back into here, I get 6 times 0 minus 1, which is a negative value. Okay, so just erasing that, that means this region will be negative. And what that means is that my second derivative here, f double prime of x, is less than 0. Okay, so it looks like in this yellow region right here, since my second derivative is positive, that means I'm concave up like that. This is concave up, and this region I'm concave down. So my graph should be concave down and look like a parabola going in the downwards direction. Now, if I go ahead and compare this to my original graph here, it looks like the value this value 1 right here, we're both there, so let me just kind of draw this value of 1 right here, and according to my second derivative right here, let me just delete this. I have a positive values over here, meaning that I'm concave up, and this part of my graph is going to be negative. So that means this region right here, I'm concave up, which matches my positive values right there, and this part right here in green is going to be concave down, which matches the negative values right there. So indeed, it was very similar to what I thought when I first started looking at the problem visually. So if I want to go ahead and finish off this problem, I would say that I'm concave up when x is greater than 1, and I'm concave down when x is less than 1. Okay, all right, so I'm going to go ahead and just erase this now, and I'll record my answer somewhere else in the problem here. Let me just delete all this. Okay, so going back to question number 1, let me just delete this here now. So basically, I'm concave up when x is greater than 1, and I'm concave down when x is less than 1. Okay, let's go on to question number 2 now. It says find the coordinates of the inflection points or points. So I believe I only have one inflection point because once I take my second derivative, which is this part right here in yellow, and if I set that equal to 0, I only get one value of x, which is x equals to 1, so I only have one inflection point. So here it is. This is 1 right here. That's where this point is right there. Now all I have to do now is I need to find the corresponding y value, and if I want to do that, I just take that value 1 and insert that back into my original question, which is right here. So I need to evaluate f of 1. All right, so this one is right here, and let's plug that in. This is going to be 1 cubed minus 3 times 1 squared, and that's going to be negative 2. So that implies that my inflection point is at the point 1 comma negative 2. Okay, let me delete all this. All right, so the point 1 comma negative 2 is right here, that green dot. So that green dot means that I'm not concave up or concave down. All right, so my inflection point here is 1 comma negative 2. Great. All right, now that finished question numbers 1 and 2. I'm just going to delete some of this so I can read the problem now. Problem number 3 now states find all relative extreme values for f of x using the second derivative test. Okay, so basically that means I need to find, let me just delete this original question here. Basically this extreme values, that basically means find all the max and min values for f of x using the second derivative test. Okay, so basically if we want to use the second derivative test, that means that my second derivative of my critical number, if that is negative, then that implies that I have a maximum value here. And if my second derivative of my critical number is positive, then that means I will have a minimum point at the value of x equals to c. Alright, so let's go ahead and apply the second derivative to this question now. This is something that did come up in one of the in-class assignments, so now let's go ahead and apply this to the problem now. Okay, so this is my first derivative right here in that box, and what I'm going to do next is I'm going to set that equal to 0. So 0 equals 2, and then I'm going to go ahead and I'm going to factor out my 3x here. So this is going to be 3x onto x minus 2. And if I do that, my critical numbers are going to be x equals to 0 and 2. So these are my critical numbers. So x equals to 0 and 2, those are like my values of c right there. So I have 2 values of c. And basically what I have to do now is I need to insert these critical numbers into my second derivative. Okay, so where's my second derivative? My second derivative is basically right here in this red circle there. So my second derivative here, let me just delete all this. Let me rewrite my second derivative here. My second derivative is f double prime of x equals to 6x minus 6. And now let's go ahead and evaluate my critical numbers here. So I'm taking this value of 0 and I'm going to insert that into my second derivative, and that's going to be 6 times 0 minus 6, and that's going to be well, this is going to be negative 6, and negative 6 is negative, so it's less than 0. So f double prime of 0 is going to be less than 0, so that implies that I have a max. Okay, so that implies I have a maximum value. So at the point 0 comma 0, I have a max. And hopefully that makes sense. Okay, so this 0 right here is this 0 right here. So all those zeros highlighted in yellow, that's the x-coordinate. And the question might be, another question that you may consider is, where did I get this 0 value? Well, all I did was I grabbed this 0 value and I put that back into my original function, which is this guy right here. So if I plug in f of 0 into this polynomial, I just get 0, right? So that's how I get this final coordinate right here of 0 comma 0. Alright, so 0 comma 0, I do have a max, and if I go back to the picture of my graph, here's 0 0, and I do indeed have a maximum value there. Okay, so going back to my critical numbers here, I've now finished off with this x equals to 0. Now I need to evaluate x equals to 2. So let me just delete this now. Okay, so if I evaluate f double prime of 2 now, so that means I'm putting my critical number into my second derivative, and if I evaluate this, I get 6 times 2 minus 6, and this is going to give me a, well, that's going to be 12 minus 6, which is 6, and 6 is obviously going to be positive, so that means that f double prime of 2, that's going to be greater than 0, then that implies that I have a minimum value at x equals to 2. Okay, and if I go back to my graph now, here's my value of x equals to 2. If I actually go all the way down, I do indeed have a minimum value. And if I want to find the exact coordinates of my minimum, I would plug in the value of 2 back into my original function there. And if I do that, I will get, well, let's do this. It's 2 cubed minus 3 times 2 squared. So that's going to be 8 minus 3 times 4, which is going to be negative 4. Okay, so this has a value of, negative 4. All right, so there you go. That completes the problem for the very first question. For the very first question, we were just using the second derivative to find where we were concave up and concave down, and we also found our inflection point, and we also verified that we had a maximum or minimum value using the second derivative test. For the second derivative test, this is something that I would definitely memorize. Okay, because the second derivative test is a combination of the first derivative, your critical points from your first derivative, and you're putting that into your second derivative, and basically if you get a positive or negative value, that will determine whether you have a max or a min. If you don't like the second derivative test, then feel free to use the first derivative test in order to verify whether you have a maximum or a minimum value. All right, let's move on now. Okay, so in this next question here, I have this graph, and I have several points, A, B, C, D, and E, and the instructions are the graph of f is shown. Okay, so this is my original graph, and determine whether f prime and f double prime are positive, negative, or 0, and describe the behavior of the graph of f at each point given in the table below. Okay, so if I look at the full set of notes here, notice that I have these values of A, B, and C, and D, which correspond to my graph. And this part right here is asking me, what's happening to my first derivative and what's happening to my second derivative at those points. Okay, so let's take a look at point A here. Now at point A, it looks like I have a relative, let's just say a relative max. I won't say absolute max because this is not a closed interval. This graph is continuing to go on forever here, so it's a made-up graph. I don't know if it's an absolute max or not, but let's just play it safe and say that we have a relative max. So that's step number 1. I have a relative max, okay? And if I have a relative max, that means I also have a horizontal tangent line, all right? So if I have a horizontal tangent line, that means that my first derivative must be equal to 0. So my slope is going to be equal to 0 because I have a horizontal tangent line. So let me write that down. I have a horizontal tangent line. Okay, so since I have a horizontal tangent line, that means my first derivative must have a value of 0. That means my slope is 0 at that point. Okay, great. What else do I have here? I guess I'm done with my first derivative. Now, in this lesson, I've been talking about concavity, and remember, concavity has two shapes. This means I'm concave down, and this means I'm concave up. All right, if I'm concave up, that means my second derivative is going to be positive, and if I'm concave down, that means my second derivative is negative. If I look at the point at A, notice that if I go from left to right, it looks like I'm concave down there, right? It looks like my concave down shape there, so that means my second derivative has a negative value there. So my second derivative here will be negative. Okay, since I'm concave down, and I'll say that my graph is concave down. Okay, and that's it. That's all I have to do that's it for that part of the graph. Section A is now done. Okay, now I'm going to skip part B and let me work on part C now. At part C, I have at this point right here, I have a relative min, right? That's the minimum value. So I'll say that I have a relative min, and once again I have a horizontal tangent line. If you have a max or a min, you will always have a horizontal tangent line, and that implies that my first derivative has a value of 0, so this is going to be 0 right here. And notice that I am taking the shape of a concave up graph, right? I'm concave up here, it matches. So if I'm concave up, that means my second derivative is positive. So this will be positive. My second derivative is positive. I'll say, since I'm positive, I'll say concave up. And you could also say that I have a horizontal tangent line. I'll just say horizontal tangent line for short. Okay, and that's about it. I'll move on to the next point. And another good point that you could analyze here is, let's look at point E now. Point E. At point E, I don't have a smooth curve. It looks like I have some kind of a cusp here. All right, so if you have a cusp at this point right there, that means it means that you can't find, it's not differentiable at that point. And if it's not differentiable at that point, then that means E, you don't have a derivative. So we'll say that your does not exist. Okay, so there's no slope at that point. Okay. But I can definitely say that this, even though I can't find the maximum, or sorry, even though I don't have the derivative at that point, this looks like a relative max. So I can definitely fill that in over here. This will be a relative max. And the only other thing I conclude right here is, let's look at the right-hand side. The right-hand side, it looks like I'm being concave up. And if I look at the left-hand side, it looks like I'm being concave down. So since I changed concavity, that means I have an inflection point, right? So inflection point means that you're changing concavity from positive to negative, or from negative to positive. So at point E, I also have something called an inflection point. All right, because I change concavity. Right, and for point E, that would also imply that my second derivative does not exist, because since I have a cusp there, you really can't differentiate that, so you don't have a first derivative or a second derivative. Okay, now let's kind of erase all of this, and now let's look at points B and D. The first thing I'm going to do is I'm going to look at the value of D right here. So let me circle this. It looks like I have a positive horizontal tangent line, so that means my first derivative is going to be positive. And if you look at point D very carefully, that actually resembles an inflection point, because if you look to the left-hand side, I'm concave up, and if I look at the right-hand side, I'm concave down, I guess. So since I'm changing concavity, that means my second derivative is going to be 0, right? So this means f will be increasing because I have a positive derivative slope there, and that also implies that I have an inflection point, so IP, inflection point. And then finally for section B right here, it looks like I have a horizontal tangent line. So if I have a horizontal tangent line, that implies that my first derivative will be 0. Okay, and basically, since you have a straight horizontal line, one other thing that you can notice is that over here on the left-hand side, I am concave down, and if I look at the graph on the right-hand side, it looks like I'm concave up. So I do change concavity. So since I'm changing concavity, that means my second derivative here has to be equal to 0, because I have an inflection point. So for B here, my second derivative is going to be 0. So I'll say that f has a horizontal tangent line, and that also implies that I have an inflection point. Okay. So one thing that you may recognize is that whenever your second derivative, whenever you have a 0 value for your second derivative, you will always have an inflection point. Okay. And it's also possible that you can have an inflection point when you have a does not exist for your second derivative. So if you do change concavity, that also means you have an inflection point. Okay, let's move on now. All right, so before I move on, I want to show you the relationship between f prime of x, f double prime of x in correspondence to the original graph f of x. If I look at this box right here, this means the second derivative is negative, so that means I'm looking at a concave down situation. And over here, my second derivative is positive, so that means I'm looking at a concave up situation. This will be concave down, and this will be concave up. Okay, so if I'm concave down, if I go back to this part right here, concave down means my graph looks like this. If I'm concave up, my graph looks like that. And if I'm concave down, my graph looks like this, and concave up, my graph looks like that. Okay, so let me just delete all this now. Alright, now let's focus on the first derivative now. My first derivative, that means if I highlight this first derivative there, that means I have negative values. So if I look at my graph, if I look at my concave graph right here, if I look at this again, where is the graph negative? Meaning where does the graph have a negative slope? Well, that's all right here, right? This part of the graph will have a negative slope. Alright, so if you combine these two factors together, your graph pretty much looks like this. Okay, which corresponds to, you know, this yellow part of the graph right there. Okay. All right, let's move on to the next box. Delete that now. Okay, so for my next box right here, this means my first derivative is less than 0. And if I look at my graph here, if I look at this graph right here again, my concave up graph here, where does this graph have a negative slope? Well, that's right there. This part in blue. All this part is all negative. So basically my graph will look like this. Okay, and I'm going to put my arrow, feel free to put your arrowhead over here at the top, or you could put your arrowhead towards the bottom there. I think it's a little bit more appropriate to put the arrowhead towards the bottom there, because usually you're graphing from left to right. Okay, but this part represents, you know, that represents this part right there. Okay, let's delete that now. Alright, so for the next part here, my first derivative is positive, so that means I'm looking at this part of the graph right here in yellow. So let me just reproduce that over here to look like that. Okay, so those parts are relatively the same, and once again, if you want, you could put your arrowhead over there. I like to graph from left to right, so I'll finish by putting my arrowhead over there. And finally, this last part here, I have my first derivative being positive, so that deals with this part right here, because this is going to be all positive, right? These are all positive slopes, so my graph looks like that, which corresponds to this part of the graph. All right, so let me just delete that, and there it is. Here's my table of possible. Sorry, if I combine my first and second derivatives, these are my possible choices that I have. All right, let's move on now. Now that we've been talking a lot about first derivatives and second derivatives, where's my derivative concave up and concave down? Let's go ahead and now apply this and actually graph a question now. So for the next problem here, I have this polynomial here, and I want you to sketch a graph of this, and I need to include all important features. Okay, so a question like this will take a very long time. One important point that you can get right away is your y-intercept. Okay, so your y-intercept will have the point 0, 4, and if you're asking me where did I get this point, well, that's this value right here. If I plug in 0 for all my x's, then basically I'm left with a value 4 there, so that is my y-intercept. Okay. So after this, I need to take my first derivative and my second derivative. I need to find where I have a relative max and a min, and I may also want to find my intervals of concave. I may also find my intervals where I'm concave up and concave down. All right, so let's go ahead and take the first derivative now, because if I take the first derivative, I can find my critical numbers. So this is going to be negative 6x squared minus 6x plus 12. And on the side here, I will take my second derivative in red. That's going to be negative 12x minus 6. Okay, so I'm going to go ahead and set my first derivative now equal to 0, because I want to find the critical numbers. So let me factor out the negative 6 here. So I'm going to just factor out that negative 6. And if I do that, I get x squared plus x minus 2. And let's go ahead and factor this a little bit more here. That's going to be negative 6. Factor that into x plus 2, x minus 1, and that means my x values here are going to be negative 2 and 1. So these are my critical numbers. All right, so let me box that. Those are my critical numbers. Okay, and how do I use my critical numbers? Well, basically you want to draw a number line here. Put those values in, negative 2 and 1. This is my first derivative, f prime of x. and that's going to equal to negative 6 bracket x plus 2 times x minus 1. And then we need to evaluate the 3 intervals. So here's one interval in yellow, and if I pick a value there, such that let's say I pick a value of 10. So if I plug in 10 here, it looks like I'm gonna have this is gonna be positive, this is gonna be positive, and that's gonna be negative. So this is gonna be all negative right here. Okay. And if I now go ahead and pick a value of maybe 0, and that represents this this blue region right here. If I plug in 0 into my my first derivative, this is going to be positive, that's going to be negative, and this is going to be negative. So that's going to give me a positive situation here, right? Okay, so sorry, a negative and negative gives me a positive, right? Okay, so let me just delete that now. And finally, let's go to my last region here in green. Let's pick a value of maybe negative 100. If I plug in negative 100 into my first derivative, this is going to be negative, that's going to be negative, and that's going to be negative. So 3 negatives, that means my region will be negative. Okay, so there it is. That right there is my first derivative test. So that means my graph is going like, down and then up, and then down here again. So that means I have a minimum point here and a maximum point over there. Okay, so let's go ahead and find the coordinates of my maximum and minimum points. So if I evaluate f of negative 2, that means I'm plugging negative 2 back into my original question, which is right here. So if I evaluate f of negative 2 here, I will get a value of negative 16. Alright, so f of 2 equals to negative 16, so that means at negative 2 comma negative 16 I have a minimum value there. Alright, and if I evaluate f of now 1, so this 1 right here is that critical number right there. So if I evaluate f of 1, meaning if I plug in 1 back into this original question, f of 1 here, if I do the math in my head here really quickly, I should get a value of 11. So this implies that I have a value of 11 here, so this would be 1 comma 11, and this is a max. Okay, so by my first derivative test, I have found my maximum and minimum values. Okay, and that's about it. You could probably do a pretty good job of graphing this, but what I'm going to do next here is I'm just going to go ahead and analyze my second derivative, because another good point that I could find is my inflection point. The inflection point is another important feature of the graph. So let's go ahead now and set my second derivative equal to 0. If I do that, I'm going to factor this. So this is going to be negative 6 onto 2x plus 1. If I do that, x is going to equal to negative 1/2. So this is like an inflection point. This is the x coordinate of my inflection point. This is not a critical number. And then what I do next here is I can basically, I want to just delete that. Okay, sorry. If I draw a number line right here, if I put the point negative 1/2 right there, then let's go ahead and evaluate my second derivative here, f double prime of x. That's going to equal to negative 12x minus 6. Let me just use the factored form, negative 6 times 2x plus 1. And if I pick a value here on the yellow region here, like a good number might be 0. So if I plug in 0 over here, it looks like that's going to be positive, and that's going to be negative. So this is going to be negative. And if I plug in a value on my blue region now, such like maybe negative 100, then that means, let me just erase this. This is going to be negative, and that's going to be negative, so this should be positive. Okay, so that means my graph is going to be concave up here like that, and over here I'll be concave down. Okay, great. And let's go ahead and find that inflection point here. So here's the value of f of negative 1/2, and I need to evaluate f of negative 1/2. And if I go back to my original question here, if I delete all this, if I evaluate f of negative 1/2, unfortunately that's going to be a bit hard to calculate. I'm just going to give it to you. It's going to be negative 5/2. So this is something that you do have to work out. You may use a scientific calculator if that helps. So f of negative 1/2 is negative 5 over 2. So what that means is that negative 1 over 2 comma negative 5 over 2, this is my inflection point. Alright, so this is another key point. And now I have enough information now to graph. I have enough information now to provide a sketch. And I'm just going to just draw a blank graph over here. Okay, so I know my y-intercept is going to be at the point 0, 4. Alright, so there's my y-intercept. I also have a minimum value at negative 2, 16. So here's negative 2 and negative 16 is down over here. So this is negative 2 comma negative 16, which is a min. So if I have a min, then my graph is going to be behaving like that. And I also have a maximum at the point 1 comma 11. So maybe somewhere over here, 1 comma 11. And I have a max, so my graph is going to look like this. And I also have an inflection point at the point negative 1/2, 5 over 2, so that's somewhere maybe over here. That's going to be negative 1/2 comma negative 5 over 2, right? That's my inflection point. So once I have all those points, we can go ahead, let me just erase these points now. I can go ahead and just connect the dots and get a basic sketch here. I'm going to connect that roughly like this, down like that, and this is probably going to come down like that. And this is probably going to go up like that. Okay, so here is a very rough sketch of my graph right here. And once again, this point right here is the point 1 comma 11. And before I finish this question here, let me just go ahead and put my second derivative number line here. So if I put a number line here with my second derivative here, I'm going to go ahead and copy. Basically, I want to take this information here and I want to drag that down. I want to drag that down over here, and I know that my inflection point is at the point 1/2, negative 1/2. Okay, so I had all these positive values over here on my second derivative. So if my second derivative is positive, that just means my graph is concave. Sorry, this is all negative. Sorry, I made a mistake here. These are all, yeah, if I go back to my original, this yellow part right here is all negative. So this is all negative right here. I apologize for that. And that means I'm concave down. And if you look at my graph right here, this yellow part right here is indeed concave down. Okay. And on the left hand side, I do have positive values. And if I have positive values, that means I'm concave up. And look at my graph. Yes, that is concave up, right? This is concave up right here. And this point right here, that's my inflection point. Okay, so that's a very good sketch of the original question. Okay, so that concludes most of the questions that I covered in the lesson. There was one more question that I just didn't have enough time. That was example number 2. And just give me a second here. I'll definitely go over this question in a few minutes. Just give me a second. Let me pause the video. All right, so let's go over this final question here. The cubic function y equals to ax cubed, I mean all of that. It has a point of inflection at the point 1, 6 and a relative maximum at x equals to -1. I need to go ahead and find the values of a, b, and c. Okay, fine, no problem. Alright, so I have this polynomial graph and I have an inflection point at the point 1, 6. So this part right here, an inflection point at the point 1, 6. So one thing that you need to recognize right away is that if you have some kind of graph, let's say this is f of x, and let's say your inflection point is right here. Your inflection point, this might be 1, 6. Your inflection point is actually a real point on your graph. So what I can do is I can take this 1, 6 and actually plug that back into my original equation, because the point 1, 6, which is an inflection point, that is actually a real point on your graph. So let's go ahead and use that information and create an equation here. So this is going to be 6 equals to a minus 3 plus b plus c. Okay, so if I take the numbers 1, 6 and put the 6 here and all the 1s for all my x's, I get 6 equals to a minus 3 plus b plus c. And if I move things around here, I should get 9 equals to a plus b plus c. Alright, so this is equation number 1. Okay, so let me go ahead and just delete this now. Okay, let's take a look at the second piece of information here. It says that I have a relative maximum at x equals to -1. Okay, so if you have a relative maximum, something like that, that means you have a horizontal tangent line. Alright, so you have a horizontal tangent line, so that means your critical number here is going to be -1. So that implies that f of -1 equals to 0. Okay, so if my original equation is y equals to ax cubed minus 3x squared plus bx plus c, if I use this fact right here, that means I need to take my first derivative here. Sorry, I forgot my prime here. This is f prime of -1 equals to 0. So if I go ahead and take my derivative here, this is going to be 3ax squared minus 6x plus b. And I'm going to go ahead and set that equal to 0. So this part right here is that part right there. And let's go ahead and plug in -1 for all my x values. So this is going to be 3a times -1 squared minus 6 times -1 plus b equals to 0. This is going to be 3a plus 6 plus b equals to 0. So this is going to be 3a plus b equals to -6. And that's going to be my second equation. Okay, so my second equation, I'm just going to put this right underneath here. This is going to be -6 equals to 3a plus b. Okay. Let's see, do I have enough information to solve this question now? We probably do. The final kind of piece of information that you need is you need to go back to your inflection point right here. And if you have an inflection point, that basically means that your second derivative is equal to 0. And ask yourself, what is this x value? Well, it's going to be the x value right there. So what that means is f double prime of 1, that equals to 0. Okay, so the final thing that you need to do here is you need to take the second derivative. So let me go ahead and just delete all this. If this is my first derivative, then my second derivative is going to be 6ax minus 6. And I know that my second derivative at the value of x equals to 1, that's going to be 0. So if I use that over here, I can just set this equal to 0. So this part right here represents that part right there. And that means I plug in x equals to 1, set that equal to 0. This is going to be 6a equals to 6, and that means a will equal to 1. So this is my third equation. So if I go back to my original, all my information here, this is my third equation. That means a equals to 1. If you go ahead and solve all this, I'm not going to go ahead and solve all that, but your values will be a equals to 1, b equals to -9, and c equals to 17. Alright, so that concludes this video. We'll see you guys in class.